Okay, section 9.1 is on square roots. Now over here on the right I have some common squared, so I have 1 squared, 2 squared, all the way up to 15. And we've already studied what exponent, when we have something squared, really what that means is that's like, for instance, 15 squared is really 15 times 15 equals 225. But a shorthand way of writing it, in more common way, is just using the squared symbol, the exponent 2. Now, in this lesson, we're going to be talking about square roots. So just like the inverse of adding is to subtract and the inverse of multiplying is to divide, the inverse of squaring something is to take the square root of it. They both use that word square. Okay, so on the far right side, I have the first 15 perfect squares. These are known as perfect squares, and I'll explain why in a second. But first, we just want to get the concept of what a square root is. The square root of a number is what number we can multiply by itself that will get that. So for instance, if I take this square root of 225, I'm really thinking what number times itself, it has to be the same number, is going to equal, oh I'm sorry, not 15, what number times itself is going to equal 225? That's what I'm trying to figure out. So I want to know what can I multiply by itself that's going to give me that? And the answer is 15 times 15. So really I'm trying to basically think backwards. What number times itself is 4? 2 times 2. What number times itself is 9? 3 times 3. What number times itself is 16? 4 times 4. So square root is really, that's exactly what it is. So there's a couple of common ones, like the square root of 49 is 7, because 7 times 7 is 49. When I say common, I mean perfect squares. A perfect square is an answer that comes out as a specific answer, like, a specific whole number. So here, the square root of 1 is just 1, square root of 4 is 2, square root of 9 is 3, because this number times itself is this here. Now I kind of have it related color-wise. Notice that these here are perfect. When we square something, we get these answers. That's also what our perfect squares end up being, okay? Now notice that there is no square root of 2 on here, or square root of 3, or 5, or 6, or 7, or 8, and then there's a whole bunch in the middle of all these as well. Because, think to it yourself, is there anything I can multiply by itself that's going to give me 2? Well, no, not really. Not that we know off the top of our head. I mean, definitely there's a decimal out there, but there's no whole number that we can multiply by itself to give us 2. We can add 1 plus 1, but we're talking about multiplying. Is there anything I can multiply by itself to give me 3? No, I can add 1.5 plus 1.5, but again, I'm not adding, I'm supposed to be multiplying. Nothing can multiply to give me 3. Nothing times itself is 5. 1 times 5 is 5. Yeah, that's true, but I'm not looking for two different numbers. I want the exact same number. 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25. That is what identifies a perfect square. So all of these ones that would fall in between here, that we just don't kind of have written in, they still exist. These are still square roots. You can find the square root of any number that's positive. Any positive number is going to have a square root. However, a lot of them are going to give you decimals when you figure out what those are. And so what we have here is our list of the first 15. We could keep going forever and ever and ever, but the first 15 perfect squares. And that's what we're going to be kind of working with quite a bit to keep in mind. Okay, so a square root, basically the definition is something like if you have m squared equal to n, then the square root of n equals m. And that's confusing a little bit when you start throwing variables in, but 3 squared equals 9, well then the square root of 9 is equal to 3. And the reason is because 3 times 3 is equal to 9. Now let me ask you a quick question. Couldn't it also be said that negative 3 times negative 3 is also 9? Negative times negative is a positive. Yeah, so negative 3 times negative 3 is also 9. And that's absolutely right. So technically, when we list our perfect squares, this square root of 1 is really positive 1 and negative 1. And we can denote that with a plus minus symbol that looks just like this. The square root of 4 is really positive 2 and negative 2, so I can write plus or minus 2, plus or minus 3, plus or minus 4. And that means it could be the square root of 16 is 4, because it could be 4 times 4 equals 16. Or the square root of 16 could be negative 4, because negative 4 times negative 4 is 16. Now for our purposes, this chapter, we're only going to take a look at the positives, but if you, in this particular section, 9.1, the first set of questions and homework involve answers in the back using plus and minus, positive or negative, and that's the reasoning behind it. So if you see it, I want you to be familiar with it, but for our sakes, we're only going to take the positive answers to our square roots. So if I say the square root of 25 in class, you can just tell me 5. Okay, so that's the general concept of a square root. Now let me ask you one more question before we move on to perfect squares. That is it possible, running out a little bit of room here, is it possible to have a negative underneath a square root? So what I mean by that is, if I pull this down, little section area, if I have the square root of -9, is that possible? Is there any two numbers that I can multiply by themselves that are going to give me -9? Well, I can do +3 and -3, but those aren't the same number. I can do -3 and +3 again. They're not the same number. So no, the answer is you can never have a negative under the square root. No negatives. Okay, if you put it in your calculator, you're going to get something that will say a domain error, which will make more sense once you start graphing them years to come. But basically, you just have to know that you can never have a negative underneath the square root symbol. Okay, never possible. All right. So square root we covered. Perfect squares, as we mentioned, these are a list of perfect squares. All of these come out to be nice whole numbers. 6, 8, 6, 7, 8, 9, 10, on and on and on. They're whole numbers. And again, this list keeps going. But again, there are square roots of 2, which if you find that, that's going to give you a decimal. Square root of 3 is going to give you a decimal. Square root of 5 is going to give you a decimal. It's 2.2360679774999, on and on forever. So there's a lot of, every number that's positive is going to have a square root. There's even a square root of 8.32. There is going to be a square root of it, but it's not going to be one that's a perfect square. Perfect square comes out to be a whole number, just like we have here. Okay, so that's that. Let's take a look and do some work with them, and it'll click more and more the more we go. So first it says you can use your perfect squares to approximate square roots to the nearest integer. So square root of 51 is not a perfect square. If I look at my list, and I know it's a little cluttered right now, but we're just focusing on this area here. You might want to make a list for yourself on like a separate note card. Square root of 51 is not a perfect square, or I can think to myself, is there anything times itself that's going to give me 51? No. 51 is actually primes. Or no, it's not. It's not prime. That's not true. But there's nothing times itself that will give me 51. So instead, I can use my knowledge of perfect squares to approximate. I can say, well, the square root of 51 is close to, that's why I use the squiggles, square root of 49. And I know the square root of 49 is 7. So I can say it's close to the square root of 49, and I know that's 7. So square root of 51 should be a little bit more than 7 probably. And I can use the squiggles there because it's not equal to it, but it's close to it. Square root of 125. Well, if I look at my list here of perfect squares, the square root of 125 would fall right in here. It's going to be closer to 121. So it's close to the square root of 121, which is 11. Square root of 67. Find that on my list, or I might just think through it. It's close to the square root of 64. Square root of 64 is 8. And the square root of 101 is close to the square root of 100, and the square root of 100 is 10. Okay? So we can use our knowledge to approximate some square roots. Example 2, it says use a calculator to approximate the following square roots to the nearest 10th. Pretty much any calculator that you find that has any extra buttons beyond add, subtract, multiply, and divide is going to have a square root symbol. That one's pretty common. There's a link to it on my website. If you go to the fun page, there's a connection to a website that has a free online calculator. Your computers come with calculators, your iPods, iPhones, whatever electronic device you're using most always has a calculator built into it, if you don't happen to have your regular school one with you. But they want us to use the calculator to approximate the following square roots to the nearest 10th. And if you're not sure how to get the square root symbol working, you can ask me and I'd be happy to help. But all I'm going to do is type in the square root of 515. I get 22.693. I'm going to round it up to 22.7. Okay, next one, square root of 79. I'm going to put that in my calculator and I get 8.88, which is going to round up to 8.9.